Okay, as I promised, this is the video for example chapter 4.2. Okay, in this video we will discuss on two example. Okay, which is first on overall heat transfer coefficient of a heat exchanger. Okay, basically we have a double pipe heat exchanger here. This one. So okay, let's read the question first. Hot oil is to be cooled in a double tube counterflow heat exchanger. So the copper inner tube have diameter 2 cm. So this one is 2 cm. The inner tube, the blue tube is 2 cm in diameter, and the thickness is negligible. The inner diameter of the outer tube, that means the shell, is 3 cm. So from the top of the grey tube to the bottom, that means the annulus space. Water flow through the tube at a rate of 0.5 kg per second, and the oil through the shell at a rate of 0.8 kg per second. So taking the average temperature of the water and the oil to be 45 degrees Celsius and 80 degrees Celsius respectively, determine the overall heat transfer coefficient of this heat exchanger. Okay, so let me show you on how to answer these questions. You also can try by your own to solve this question. Okay, first thing first, we need to have the properties for each of the material, which is water and also hot oil. So properties of water. So water is at 80 degrees Celsius. Water is at 45 degrees Celsius. So in the properties table, you can refer to table A9 to get the properties. For example, like density, conductivity, Prandtl number, and also kinematic viscosity. So from the property table, we get the density 990.1 kg per m cube. For K, we get 0.637 watt over meter dot Kelvin. So for Prandtl number, we have 3.91. And for the kinematic viscosity, basically you can calculate it by using formula viscosity over with density. So the answer would be 0.602 times 10 to the power of 6 meters squared per second. Okay. Next, we find the properties of oil. Oil at 80 degrees Celsius. So for the oil, we can refer to table A13. So please make sure you refer to correct table in order to get the correct properties. These properties you will use inside the calculation. So it is really important to get the correct properties from the correct table. So the density of the oil is 852 kg per m cube. So the conductivity is around 0.138 Okay, so for the Prandtl 499.3, for the kinematic viscosity 3.79 times 10 to the power of -5 meter squared per second. So this question need you to determine the overall heat transfer coefficient. So basically we can use the formula of 1/U equal to 1/Hi plus 1/H0. So basically this is the double pipe heat exchanger. So we need to determine the hydraulic diameter for a circular tube. So first thing first, we do the cool water part first, the inner tube first. So for the inner tube, we need to calculate the hydraulic diameter. So for the inner tube, hydraulic diameter would be equal to the inner diameter, which is D inner, which is 2 cm. So convert in meter, become 0.02 meter. Okay, then we need to calculate the Reynolds number. But inside the Reynolds number, you need to have information on the velocity, right? So you need to calculate the velocity first. Okay, how we can calculate velocity? We can calculate by using equation rho equal to m times V, which is density, mass flow rate, and also our volumetric flow rate. Okay, so from this, rho equal to mass flow rate, so we can expand this V, velocity times with area. So in order to get the velocity, we will have so sorry. Sorry, my mistake this one. M is equal to rho V. So this rho is in kg per meter cube. So okay, yes, correct, this one. So from we have this mass flow rate and also a volumetric flow rate. So I want to expand velocity times A. So in order to get velocity, we will get the formula like this. Rho A. Okay. So all the information here we have mass flow rate, density, and also area. We need to calculate first. Okay. So let we put inside all the information given. So for the M here, we have 0.5 kg inside the tube, right? The flow rate 0.5 over with 0.1 times with pi d square. So d square is 0.02 square over 4. So the answer would be 1.61 meter per second. Okay, so now we need to calculate the Reynolds number. So we use this Reynolds number formula, velocity times with the density over kinematic viscosity. So just put the value in 1.61 times with 0.02 over with 0.602 times 10 to the power of negative 6. The answer would be 53490. So this value is greater than 10,000. That means the flow is turbulent. Okay. So, now for the turbulent flow in tubes, we can refer to this formula. So for your information, for the first Peterkopf equation, is referring to smooth tube. So for this condition, we can use Dittus-Boelter equation. So inside the tube, there is a heating condition, heating process occurred. So we need to this end substitute with 0.4. Okay. So to calculate the Nusselt number, Nu is equal to H D over K, right? Is equal to Prandtl number, Nusselt number formula 0.023 time with R. Time with RE 0.8 to the power of 0.8, Prandtl to the power of 0.4. So substitute the value of RE and Prandtl number. You will get the value is 240.6 for Nusselt number. So now we have to solve for H. So this would be HI. So we have D and also K. HI you will get around 7663 over meter squared dot K. Okay, so complete for the inner tube. So now we move to outer tube. So basically same, we need to get the hydraulic diameter first. So I mark this one is 1, this one is second. So hydraulic diameter for the outer tube is quite different because we need to consider the annulus space. So you can refer to this flow through the tube annulus. Okay, basically if you want to get the hydraulic diameter of annulus, you need to use this formula. DH is equal to D outer minus with D inner. Okay. So D outer is 3 cm, D inner is 2 cm. So the difference is 1 cm, convert in meter, become 0.01 meter. Okay, so complete for hydraulic diameter. Now you need to calculate the same like previous step. You need to calculate for the V. So now I directly input the value for V. So V here we have mass flow rate 0.8, right? Okay, 0.8 over with the density is 852 times with pi d square over 4. So here D you need to input is hydraulic diameter. So pi d h squared over 4. So dh, the formula is d naught minus di. So you need to fill in the value of d naught and di. So d naught is 0.03. Squared minus with 0.02 squared over with 4. So the answer would be 2.39 meter per second. So the Reynolds number formula VD over V. So please remember this one. If you need to calculate the area for the annular space, you need to put in the DH formula. This part. So now for the Reynolds VD over V. So in here you can directly put the DH value, which is 0.01. Okay, 2.39 times with 0.01 over with kinematic viscosity is around 3.79 times 10 to the power of -5, and you will have Reynolds number around 630. So this value is lesser than 2300, then the flow is laminar. Okay, I need to take this space to calculate the Nusselt number and also heat coefficient. So we have to assume that this flow inside the annular space is full developed. So the Nusselt number that we need to consider is the Nusselt number on the tube side of the annular space, which is NUI, inner Nusselt number. So in order to get the inner Nusselt number, we need to calculate the ratio of DI over DO. So DI over DO is 0.02 over 0.03. So the ratio is 0.667. So after we obtain this value, we need to go back to the slide flow through tube annulus. So in here we get 0.667, right? So the value is in between here. So you need to do interpolation between this value. So X will be here. Okay. After performing the interpolation, you will get NU is equal to 5.45. Okay. Okay, referring back to the flow through tube annulus slide. Okay, because we want to know the heat coefficient of outer part, which is annular space, we need to using this formula. So rearrange H naught K over DH dot NU. So input the value of K, which is 0.138, time with 5.45 over with hydraulic diameter is 0.01. So the value you will get is 75.2 watt per meter squared dot K. Sorry, let me delete back. It's not clear. Okay, so we already get HI and H naught. We need to substitute into this equation. So let me use, sorry, I don't have enough space to write the equation, so I think I take this space. U is equal to 1 over 1 HI plus 1 over H naught. So just substitute the value of HI and H naught. You will get U is equal to 74.5 watt meter squared dot K. So that's all for this example example 1. But I need to inform you one more thing here. Why we directly take this formula, because at this part already mentioned, the thickness is negligible. When the thickness is negligible, we can directly use this formula according to my previous slides inside the previous video. Okay, so now we move to example 2. So this example 2 is quite simple. So let's read the question first. A double pipe, shell and tube heat exchanger is constructed of a stainless steel, K equal to 15.1. Inner tube of inner diameter di is equal to 1.5 cm and outer diameter is 1.9 cm and outer shell of inner diameter is 3.2. So please not confuse with all this diameter value. So di is in here. The arrow show the di, and d naught is the outer of the tube. So the outer of the shell is the annular space from here to here is 3.2 cm. The convection heat transfer coefficient is given to BHI is equal to 800 on the inner surface of the tube and H naught is 1200 on the outer surface. For a falling factor, RF inner is 0.004 on the tube side and falling factor outer is 0.001 on the shell side. So you need to determine the thermal resistance of the heat exchanger per unit length and the overall heat transfer coefficient UI and U naught based on the inner and outer surface area of the tube respectively. So basically the first question, you need to determine the thermal resistance that we cover in chapter 2. So okay, here R is equal to 1 over UA as we write down back the equation that I mentioned inside the slide inside the previous video. Okay, so it's equal to 1 over HIAI. So this one is a convection part, and so this equation you can directly refer back to your slide previously. So in this question, we consider both falling factor inside and outside. Sometimes in question, maybe they will mention the outer part falling factor only. So that one you need to only calculate the outer part. If in the question inform you or ask you to consider only the inner part, then you need to calculate the inner part only. So depend on the question. So here is ln. So ln d naught over di is our heat by conduction at the tube side, 2 pi KL plus with RF naught over A naught plus with 1 H naught A naught. So H naught A naught is our convection part. So first thing first, calculate your area first. You have two area which is AI and A naught. So surface area you need to calculate pi DIL is equal to, so the inner is 0.015 in a meter. So we can assume, because inside here they didn't provide you with the length of the pipe, so you can assume the length of the pipe is 1 meter. You can use the other value also, but the easiest is you use 1 meter. So it's equal to 0.0471 meter squared. So E naught is equal to pi D naught L is equal to pi 0.019 times 1 is equal to 0.0597 meter squared. Okay, so substitute all the value given and also calculated here into this formula from here to here. Okay, R is equal to, first is convection 1 over, given is 800 time with AI, which is 0.0471, plus with the falling factor, inner falling factor is 0.0004, over with AI 0.0471, plus with ln D naught is 0.019, over with 0.015 over 2 pi, K is 15.1, L is 1. So plus with the outer falling factor is 0.0001 over with A naught 0.0597 plus with 1 over H naught 1200 times with A naught 0.0597. So the answer would be, okay, let's solve first this one, all of this. So for the convection, first is you will get 0.02654 plus with second one, the internal falling factor 0.00849 plus with 0.0025 plus with 0.0168, so plus with 0.01396. So basically the bracket, you can only put the bracket here and here. Please don't follow me because I just want to differentiate it one by one. Afraid that you will get confused, but in your real calculation you can just put the bracket here, this value, plus this value, plus this value, plus this value, plus this value, and close this bracket here. So the answer would be 0.0532. Okay, now so this is first question A. Now we need to calculate the overall heat transfer coefficient. So B, we need to have UI and also U naught. So R is equal to 1 over UI AI. So we calculate UI first, rearrange this formula, we will get UI is equal to 1 over R AI. So just, sorry, this one the units is degree C over watt. So just substitute this value into this part and AI value. UI you will get 399. Please please, in your calculation, you need to show you substitute the value. Don't simply jump to the last answer. You need to show one by one. So for U naught R over E naught, and the answer 315 watt meter squared dot K. Okay, so finish for example 2. So I hope you will you can understand on what I am explaining before, and please try to do these two example in order to for you to get the understanding on this subchapter 4.2. Thank you.